Swayam Prabha. Digital India. Educated India.
Hello and welcome back once again. In the previous lecture, we were talking about the conditions that can lead to either particle pushing or engulfment. So, the thermal conductivity ratio decides whether the interface will be having a planar geometry like this, or it will deviate from a planar interface and take up a shape either like this, like a convex kind of shape, or whether it will be concave. And based upon that, the particles can be either pushed or engulfed. Pushing will lead to clustering or segregation of the particles along the interdendritic region, and engulfing, on the other hand, will lead to uniform distribution of the particles in the grains. Okay. So it's about this radius of curvature that you have along the interface, whether it is convex or concave, that is going to decide the distribution of the particles. So let us probe little more into that as to what is this radius of curvature and how it is related to this interaction between the solid liquid interface and the particle. So we are going to take the help of this particular diagram in order to understand this interaction and the role of this radius of curvature that develops along the interface. Okay, so let us consider a spherical particle of radius r. So there is a relative motion between the particles and the interface. The interface is moving because it's a growing interface. The solid is forming now. So the interface grows and the particles also move. So the particles have a relative velocity with respect to the melt. So that velocity is v. This line represents the melting point of the matrix metal. And as we have discussed before, the interface follows the isotherm of the melting point, and the thermal gradient is in this direction. Which is basically the heat flow direction. And the separation between the interface and the particle at x equal to 0 is d. So here is the x direction. So this point is x equal to 0, right? So d is the distance between the interface, or the separation between the interface and the particle at x equal to 0. Okay, so that's what you see in this diagram also. So considering this, the radius of curvature, that is this Ri, can be given as follows. where A is a function of the thermal conductivity ratio alpha and given as follows. And B is equal to 1 plus D by R whole cube. So from here you can see that when D is much smaller than R, then B tends to 1, and therefore Ri will be equal to this. Right, which comes down from this equation. Let us call that as equation 1. And if you replace A in terms of alpha, and from here we can rewrite equation 2 as this. Right? So now again you can see the effect of alpha on the curvature of the interface and whether it will be developing a bump or a trough. That can also be seen from this equation 3. Okay. For alpha less than 1, you can see that Ri is less than 0, and therefore the interface will develop a bump. When alpha is equal to 1, then Ri tends to infinity, which means it will be a planar interface without any curvature. And when alpha is greater than 1, you can see from here again that Ri is greater than R. That means it will develop a trough at the interface, which you can see over here from this diagram as well. Okay. When Ri is more than R, then only this trough develops, and this will lead to engulfment of the particles. Whereas development of the bump leads to pushing of the particles. Okay. And apart from this interface curvature, there is one more aspect which will affect the distribution of the particles, and that is the forces acting on the particle. This also needs to be considered when you talk about particle distribution, because this will also going to have an influence on how the particles will be distributed, or whether they will be pushed by the interface or engulfed by it. Okay. So engulfing or pushing will also depend on the forces acting on the particles. So we can go back to this diagram again and look at the forces acting on the particle. So basically there are three types of forces acting on a particle, which is having a relative motion with respect to the melt. And these forces are as follows. You have the gravitational force, let us call that Fg. The drag force, Fd, and the force due to interfacial energy, which is basically the molecular force or the van der Waals force that develops as the interface approaches the particle. Gravitational force Fg is nothing but mg, where m is the mass of the particle. So if you consider a spherical particle of radius r, this will be given as 4 by 3 pi r cube, which is the volume of the particle multiplied by the density rho, that's m, into g. And since we are talking about a relative motion between the particles and the metal, the molten metal, here instead of rho you will have the difference of the densities, delta rho. Okay. So from here you can see if delta rho is greater than 0, that means density of the metal is more than the density of the particles. Then Fg will act upward and will lead to pushing of the particles. Right? So this Fg acting upward is not good for uniform distribution of particles. This will rather lead to pushing or clustering of particles. Now let us come to the second one, that is the drag force. And that will be given by the Stokes law. As Fd equal to six pi eta Vr, where eta is the viscosity of the melt. And when d is much smaller than r, then it has been shown that the drag force will be given as this for a planar interface. And for a non-planar interface, the interface is assumed to be part of a spherical surface of radius Ri. And the drag force in that case will be given by the following expression. And we have seen before that this one is equal to alpha, and therefore Fd for a non-planar interface is given as this, which primarily arises due to the flow at the interface behind the particle. Fd is always conducive for engulfing. However, for a concave interface corresponding to alpha greater than 1, Ri is greater than 0 and the drag force is greater compared to a planar interface. On the other hand, for a convex interface, that is when Ri is less than 0 corresponding to alpha less than 1, the drag force is lower compared to a planar interface. Now the third one is the force due to interfacial energy A phi arises mainly due to difference between solid particle interfacial energy and the solid liquid interfacial energies. So if you look at the expression for A phi, it includes this delta sigma term which is given as this, wherein delta sigma naught is the difference of those interfacial energies. Sigma Sp is the solid particle interfacial energy, sigma Sl is the solid liquid interfacial energy, and sigma Lp is the liquid particle interfacial energy. And the term A naught is the sum of the radii of the surface atoms of the particles and the solid. And the exponent n varies from 2 to 7. So for a planar interface, this is the interfacial force. If we replace delta sigma in terms of this particular expression, and for a non-planar interface, the alpha term has to be included into that equation. So A phi in that case will be given by this particular expression. when A naught plus D is much less than R. So for alpha greater than 1, a concave interface develops and A phi is increased. On the other hand, for alpha less than 1, a convex interface develops and Fi is decreased. And you can also see that for delta sigma naught greater than 0, Fi is conducive for pushing and vice versa. Now, it has been also suggested that there is a critical velocity of the solidification front which decides the engulfment to pushing transition. So this critical velocity is a function of the particle size and the temperature gradient. For a critical separation between the particle and the interface, which is given as A naught by n minus 1 Vc is given as this one for n equals to 2 when dc becomes equal to A naught. Below the critical velocity, the particles are pushed by the solidification front, resulting in their segregation in the interdendritic regions on solidification. On the other hand, above the critical velocity, the front grows around the particles and engulfs them, leading to distribution in the grains. Right? So apart from the previous factors that we discussed, that is the nature of the interface and the forces acting on the particle, the critical velocity of the solidification front will also influence the pushing and engulfment of particles and thereby affecting the distribution of the particles in the final solidified composite. And with that, we come to the end of this lecture. Thank you for your attention.